Hello, I want to thank everyone for joining us today. My name is Mark Baker, and I have Chris Schroeder on the line as well. Um, my background with Integra Electronics is business development, and Chris Schroeder is a mechanical engineer from Stanford University, and is going to be helping me co-host the show. Today's webinar, we're going to be talking about overview discussions and basically just understanding the basic working principles of a light pipe. Over the years, we've had many experiences with engineers developing light pipes, and from the basic sense, a light pipe design is fairly simple, but can get fairly complicated easily without taking into consideration some of the basic design principles. And this is the principles that we're going to be discussing today. So what is a light pipe? And I'm going to hand this over to Chris to kind of go through the basic side of a light pipe design. Chris, any comments?
Yeah, sure. So, I mean, essentially a light pipe, gives the engineer, the designer, the ability to take light from a source where it's conveniently located, like on a board or, near the power source, and have it come out where it's convenient for the user to see it, usually at the control panel or, some other place. And so sometimes those things are very close together, like the image shown here, the board's only half an inch away from the panel. But at other times, of course, the panel could be several inches or even several feet away from the light source. And so the light pipe is just a convenient way of getting the light from point A to point B without having, in a fairly efficient manner to get a lot of the light from the light source to the light exit. Back to you, Mark.
Sure, and then so with that basic understanding, there's a principle behind that called Snell's law, and basically Snell's law is to discuss when light travels in a reflective boundary between two mediums, the rays are refracted when crossing the boundary. And there's kind of an example here on how Snell's laws work, and I'm going to let Chris kind of go into a little bit more detail on the state of Snell's law.
So Snell's law essentially, from a practical point of view, it allows you to do one thing, and that is it allows you to have light reflect inside a light pipe. The physics of how that works is not that important. The basic idea to keep in mind, though, is that as long as you're going from a material that's dense, like glass or plastic, clear plastic or something like that, or water for that matter, to a material that's less dense, like air or a vacuum, the light wants to basically stay inside the denser material. And as long as the light is hitting that boundary at a large enough angle, the light will reflect inside the medium and not escape from the medium. And so this is basically the physics that we take advantage of to create a light pipe. So the two things that are important to remember is, one, there's a critical angle that the light hitting the boundary has to be beyond this angle, which in glass and plastic is typically about 49 degrees away from the vertical. So as long as the light's hitting from 50, 60, 70 degrees off angle, off axis, the light will reflect back into the pipe. The second thing to keep in mind is this only works when what's outside of the light pipe is air or vacuum or something else of some kind of a gas. If your light pipe is going to be immersed in water, it's not going to work at all because the light will just simply go right on through. And that's pretty much it.
All right, and thank you, Chris. And so also over the years, we always have questions with engineers asking us, well, what's the light loss between the LED and the light pipe? And a good basic light loss, or in this case called Fresnel loss, is about 4%. So from the light source to the light pipe in itself going through the air and being captured by the light pipe, you can kind of configure a minimum of 4% light loss. And we'll talk a little bit about that through the flux coupling. There's basically three design challenges to be expected when designing a light pipe. And so flux coupling is actually taking the LED and the light pipe and then finding the best method to couple. In a perfect world, you can actually epoxy the LED into the light pipe and make it one component, but that's not a really practical approach for most designs. And therefore, the light pipe and LED tend to have to be separate. The effective flux coupling to get the light from an LED into the lamp guide with minimal loss would be to have the surface of the light pipe contour with the LED. So for instance, here on the top left diagram, you see a 5mm LED light pipe going into a flat surface. That's not necessarily an ideal area. A much better capture would be to have the LED slightly concaved to the light pipe, and then you can kind of figure maybe an 8% Fresnel loss in air gaps, whereas this one here we're showing more of a 10% just of light loss. So there's pretty extensive light loss when you have the light pipe flat and not contouring to the LED. And Chris, has any comments you want to add to that? Whoops.
Not really. I mean, yeah, basically is the light has to get into the light pipe in order to come out the other side. So, as Mark indicated, it's pretty important to design the interface between your light source and the light pipe. Go ahead.
So again, this is a kind of a better example of flux coupling. Having a very smooth surface of the light pipe, high polished, is absolutely critical. Therefore, you get the most capture from the LED. Again, this is a surface mount LED in this example, and you see that the surface mount LED is flat, very close to the light pipe, and it's capturing quite a bit of the light output of that LED. 20,000 spacing or less is ideal. Anything over 20,000, you start to get more flux loss. So that's a good rule to kind of keep in mind when you're designing a light pipe, to make sure that as close to the LED as possible is the best overall design practice.
Mark, if I could interject on that slide.
Oh, sure. Go ahead, Chris.
Yeah, there's one thing I've noticed in working with designers over the years is that people tend to make an assumption, and this diagram sort of shows it too, that the light is all going sort of in a straight kind of all vertical and is really nicely headed right down your light pipe. And in practice, that's generally not true. The surface mount LEDs in particular are a challenge because the light, there's no lens, typically there's no lens or focusing on the LED itself. And so the light is actually coming out, 60, 70, 80 degrees off axis. And, some of it, of course, is coming straight up, but there's a lot of the light is coming in at a wider emission angle. And so, the light going through the light pipe is not all just going smoothly straight down the middle. And this becomes important later when you talk about how to channel the light through the light pipe and out to the other end. Thanks, Mark.
Okay. Here's the example of kind of taking a light guide around corners. Now, we spoke mainly about straight light pipes, but more than not, applications require the light pipe to bend. So here's kind of a basic understanding of bending a light pipe. It's really important to think about where the bend is. In this diagram, you can kind of see that there's a minimum bend radius 2 times the diameter of the thickness of the light pipe. So what this does is it allows the rays to then be captured and bend around the light without having light exposure to be too effective on the corners.
Yeah, and then what's critical about the bending is just to keep in mind that 2x radius is really important. Like I mentioned earlier, the physics requires that the light hits the boundary. Anytime it bounces off the wall, it has to hit at an angle greater than about 50 degrees. Greater than 40 degrees to be a complement to 50 degrees. And as you're going on the corner, that angle tends to get smaller and smaller. So the tighter the radius, you're going to hit at less than that angle, and a lot of your light's going to escape around the bend. A good way to check this, and in fact a good way to check the efficiency of your light pipe in just about any way, is if you have a light pipe and you just set it up and turn the light on, if you see light anywhere coming out of the light pipe, then that's obviously light that's getting lost and is not making it to the other end of the light pipe. Thanks.
Okay. So we talked a little bit about capturing the light, flux loss. What about exiting the light? What kind of features should you be thinking about when you're incorporating the area where the light actually exits? And here's a diagram that talks about diffusing the end surface. There's many different ways of diffusing it. One would be to actually just kind of have a milky surface using a mold diffusion technique, or actually adding Fresnel lenses to that and to help disperse the light. But the idea is to disrupt the light waves so that they have a much wider viewing angle, whereas the capture area, you want to have it being more of a narrow angle so that the light isn't attracted up through the light pipe. And Chris, any comments on the exiting of the light pipe?
Just something really basic, and that is typically light pipes are used for one of two purposes. They're either used for indication, and when you just want to be able to see that the light is on or off way back inside the device, in which case a diffused exit's a great solution because it'll give you the broadest angle that a user could see the light and know that the light's on or off. Of course, the other purpose is actually to use the light coming out of the light pipe to illuminate some other object that's nearby. And then in that case, you're probably not going to want a diffused light pipe exit as much as you're going to want some kind of a lensed exit that will focus the light onto the areas of interest. That's all. Thanks.
Okay. So a kind of an overview of the physical attributes of a light guide would be to have a smooth, flat, or concave contour to match the LED lamp. That's critical because that's going to minimize flux loss. Also have a optical clear, highly smooth mirror finish of the exterior. This is then keeping the light rays contained within the light pipe. And then on the exit area, have a diffused surface to exit the light. Helps disperse the viewing angle. So we talked a little bit about the designing the light pipes and just a very high-level overview of the designing process. Let's kind of talk a little bit about the molding techniques and considerations. This is almost equally as important as the light pipe design itself. Finding a good molder that can develop a tool that will be defect-free and provide the right type of extraction with minimal sinkage of the parts is absolutely critical. Most molders do not have light pipe design experience and have a very different way of approaching light pipe design. Or light molding, I'm sorry, molded tooling design in regards to developing a tool. Chris, is there anything you want to add on to the tooling aspects for light pipes?
No, I mean, that's a great description, Mark. And the kinds of pitfalls you end up with is, molding a good design will take in mind things like sink, surface characteristics, the ability to actually inject the plastic into the mold, and these all have problems. If you don't have a good surface finish, like Mark mentioned, the light pipe won't be very efficient. Additionally, if you get any bubbles into the part, which we've had problems with in the past, that of course will cause problems. Thirdly, if you have sink, the surface that you thought was a flat cylinder will end up having, dimples and surface defects in it that will, so it's not only important to design the mold to the part properly, but also processing needs to be, you need extra attention paid to processing the parts for a light pipe as well.
Okay, okay. Yeah, thank you, Chris. We do have one question from a listener. What is the reflective paint help on the light pipe? How much can we expect the reflective paint actually helping on the light pipe?
So if reflective paint, I'm assuming it's some kind of a metallic, like a mirror finish type of thing. And I don't have a lot of experience with that. It seems like it would work fine, but I want just like to keep in mind typically those types of metallizing is done not so much with paint, but with like vacuum deposition, and it can just be quite expensive. But other than that, if you've got a processor that can give you a light pipe with a metallized finish on it, that's a great way to improve the efficiency of a light pipe.
Yeah, let me add a little bit to that. Typically, when we design a light pipe, we try to minimize any use of reflective paint just for the fact that it adds cost and expense to the process. The basic design principles that were kind of laid out in a little bit more in depth, if followed, actually reduce the chances of having to use reflective paint. In most cases that we've seen, the use of reflective paint would be when a design engineer developed a product that physically isn't capable of doing what they want. The design is so abstract that they have to use reflective paint to help manage the light around the light pipe. to get the performance, and that ultimately isn't preferred. Now, with that said, there are certain applications like backlighting and display lighting that you have to use reflective paint. And in that process, it's expected. But in a general light pipe design used for an indication, reflective paint is more or less a Band-Aid to kind of cover up design flaws. Talking about the molding, let's discuss a little bit about the plastic selection options. And here's a typical list of more of the popular Lexan plastics. Depending upon the light pipe, it can be, we're mainly talking about indication applications, but you can also go the opposite direction where the light is coming from the exterior and it's going down into a sensor of some sort that's measuring the light. In that case, 10% glass-filled medium flow Lexan is probably going to be the preferred material, and that would be the HFD 4471 by Sabic. An injectable good quality plastic with UV stabilizer for outdoor applications, good for indication applications. The LX or LUX 7189 plastic is a preferred material, and this is kind of a mid-grade acrylic-based light pipe. And then oftentimes customers want to do more of a polycarbonate just because it's easier to mold. It's going to be used in outdoors, and maybe there's a 94 VO rating that needs to be established with this particular part. Then the Lexan 945A polycarbonate is a good resin. But this kind of gives you just a basic overview of the types of plastics that are available out there. Talking a little bit about prototyping and SLAs, you know, both Chris and I have had experience, Chris obviously more so in regards to light modeling. Light modeling is a good way to start with a very complex design where you really kind of need some design tools to kind of guide you through the process. The challenges with light modeling can get very expensive very quickly. The software is expensive. Most of the light pipes that we run into are more used in indication and can have more of a basic approach where you can use an SLA to kind of help manipulate the light and give you an idea on how the light pipe works. Chris, is there any thoughts on the prototyping and SLA aspect of light pipe design?
My only comment would be, like Mark said, you know, an SLA is typically fairly cheap compared to a lot of light modeling. So if your design is, you know, reasonably simple, then modeling is probably not the best way to go. You can probably make just as much progress as quicker and for less money by doing prototypes. And one thing to keep in mind that with there's many different technologies available right now for doing 3D printing, and SLA, at least so far to my knowledge, is about the only way to go as far as light pipes, because it produces a part that is solid and has no, you know, internal features to it. If you use a traditional 3D printer like a MakerBot or something that you can buy off your desk and put on your desk, it may offer a clear material, but once you actually print with the clear material, the parts are not clear. So I just wanted to throw that in there. Thanks.
Yeah, no, thank you. That's a good point. One of the things that Integra does very well is we work with specific suppliers that do SLA water clear, high quality light pipes. So if there is any interest in pursuing that with us, feel free to contact me, and we'll be more than happy to put you in contact. A little bit about Integra Electronics is we're a local Southern California-based distributor. However, we have national presence. We sell all over the United States. The company was established in 1998. We sell a lot of passive and electromechanical products, and you can visit us on our website at integrasmp.com. But more importantly, we're here to kind of help our customers with designs. So if there's any questions about today's webinar that you'd like a little bit more advice on, or would like to consult with Chris, he's available for that. We'll be more than happy to put you in contact with Chris. Really, we're here to help you. Regarding any SLA requirements, we'll be more than willing to work with you. We can provide design guidance again. and we also like to work with our suppliers on more complicated issues. So if there's anything that you're working on that you feel you need to have a high level of support, we'll be more than happy to put you in contact with Chris and his team to help work through those challenges and issues. Again, thank you for your time. We appreciate it. Feel free to give us a call with any questions at 888-893-4447. I'm Mark Baker with Chris Schroeder. Have a great day.